we're starting the afternoon with our first keynote. And it is really an honor to welcome Pierre Lévy. Pierre is a philosopher, a cultural theorist, and a media scholar. So we're getting a little bit out of our technological comfort zone to explore knowledge, what it means to understand and know. Pierre is a fellow at the Royal Society of Canada and a research associate at the University of Montreal. He has published several books on the impact of technology on society. And Pierre's current project focuses on the development of an information economy meta-language called IEML that I recommend you to take a look at. I don't think Pierre will talk a lot about this in the talk.
I will speak about it.
Great.
Sorry.
But he will speak about it. So Pierre, the stage is yours. Thank you for coming.
Good afternoon. It is an honor to be here at the Knowledge Graph Conference. And I wish to thank François Scharf and the organizers for inviting me. As you know, today the whole world is rushing towards statistical AI, neural models, generative AI, and so on. But we know here in this room that we still need symbolic models, or if you prefer, knowledge graphs, especially in knowledge management. But why exactly do we need symbolic models in addition to neural models? Because symbolic models represent knowledge in an explicit way, which has many benefits like transparency, explainability, reliability, and so on. In this talk, I'm going to advocate for semantic or conceptual interoperability between knowledge graphs. And I will present briefly, not in detail, I will present briefly IEML, a language that I have invented at the Canada Research Chair in Collective Intelligence at the University of Ottawa with the help of my team of engineers. Being familiar with the field of knowledge management, you know that there is a dialectic between implicit in blue and explicit knowledge in red. But is there a fluid dialectic between knowledge graph and neural models today? Let's analyze the situation. There are currently two prominent ways to process data for knowledge management, with neural models based mainly on statistics for decision support, automatic understanding, data generation, and so on. And also with symbolic models based on logic and semantics for decision support, advanced search, etc. These two different approaches correspond to two different engineering cultures, but they are slowly melting today. Because of their advantages and disadvantages, people are trying to combine them, and there are several, almost all sessions in this conference that tackle the problem of their combination. I will propose my own version of this combination at the end of this talk. Now let's clarify the difference between neural and symbolic models and compare them to neural and symbolic cognition in human beings. The big plus with neural models is their ability to automatically synthesize and mobilize a huge digital memory just in time or on demand, which is, of course, impossible for a human brain to do. But that their pattern recognition and generation process is statistical, meaning they can't organize a world. They can't conserve objects. They have no understanding of time and causality or space and geometry. And these neural models cannot always, for example, recognize image transformations of the same objects the way living beings can. By contrast, real living neurons can do things current formal neurons can't do. Animals' brain, even without having symbolic models, just with their neurons, can model the world. They use concepts, not explicitly, of course, they are animals, but they have models that organize their behavior. They conserve objects despite their transformations, and they grasp time, causality, space, and so on. As for human brains, they are able, in addition to all these feats of animal brains, we are able to run symbolic systems with our brains. And in fact, the neural models of artificial intelligence cannot really run symbolic systems like languages, music, and so on. Now let's look at symbolic models. The positive aspects of artificial intelligence symbolic models or knowledge graphs is that they are explicit models of the world, more precisely a local, practical world, not the world in general. It's almost impossible, of course. Not almost, it's completely impossible. They are, in principle, self-explanatory if the model is not too complex, and they have strong reasoning abilities. So they are reliable. But there are two main weaknesses in current symbolic models. First, their design is time-consuming, so they are expensive in terms of specialized labor. They have neither concept, I was speaking about object conservation when I evoked the animal brains. But if we look at symbolic models, they don't have concept conservation or relation conservation between ontologies or domains. And in any given particular domain, every concept and relation have to be logically defined one by one. And this is not the way we are thinking or even communicating. While there is interoperability at the file format level, like RDF or JSON-LD and so on, this interoperability does not exist at the semantic level of concepts. And this compartmentalizes knowledge graphs, hindering collective intelligence. By contrast, in real life, humans coming from different trades or knowledge domains understand each other when they share the same natural language. Sometimes you need a little bit of dialogue to understand other people, but with dialogue, we are able to understand each other. In human cognition, a concept is determined by a network of relations that is inherent to natural languages. What do I mean by this? What is this network of relations? And why am I pointing out this in this talk? Because I think that current symbolic AI is missing the semantic aspects of human language. Let's do a little bit of linguistics here so we can understand this flow of symbolic AI better. And here comes the original part of this talk. Any natural language weaves at least three kinds of semantic relations: interdefinition, composition, and substitution. Interdefinition, see the top of the slide, any word is defined by a sentence which involves other words. Other words themselves defined the same way. For example, a dictionary involves a circular or tangled interdefinition of concept. Second, there is the composition. Thanks to grammar rules, we can compose original sentences and understand new meanings. For example, if I say, I am painting the small room in blue, you are automatically reconstituting the grammatical tree of the sentence because you have the grammar. It is embodied in your brain. And then there is the substitution relationship, because not every word in a sentence can be replaced by any other. There are rules for possible substitutions, and these rules contribute to the meaning of words and sentences. Well, I am painting, you can replace I by you, by they, by Peter, and so on. So the small you can replace by big, medium, narrow, etc. And blue you can replace. So all these possible combinations, substitutions, are a paradigm. Okay. So we have grammar, you have paradigms, and you have interdefinition. And all this is part of the language itself. You don't have to redefine it anytime you speak. These relationships of interdefinition, composition, and substitution between concepts don't have to be defined every time you speak. It's included in the language. And this is what I call linguistic semantics. It's very important to distinguish linguistic semantics and referential semantics. Linguistic semantics is the relationship between the concepts that are parts of the language. Referential semantics is the relationship between a proposition and a state of things, and this is outside of language, okay? Or the relationship between a proper noun and an individual. This is also referential semantics. And very often there, sorry? Linguistic semantics is different from grammar, okay? Because grammar is about the different roles, grammatical roles in a sentence and how they are organized. But in linguistic semantics, you have also the dictionary, the thesaurus of the dictionary, and the paradigms, okay? For example, the conjugations and so on. So it's not only the grammar, it's something bigger. So it's really convenient because all these relations between concepts are part of the language, and you don't have to redefine all these things when you speak and when you communicate or when you model a domain, for example. But unfortunately, we don't have any of these semantic functions of interdefinition, substitution, grammatical organization, and so on, when we build current knowledge graphs. And this is where the IEML meta-language could improve symbolic AI and knowledge management. To support my argumentation for new methods in building symbolic models, you have to keep in mind the difference between linguistic semantics and referential semantics. If linguistic semantics weave relation between concepts, why can't we use natural languages in symbolic models? We all know the answer. Natural languages are ambiguous grammatically and lexically, and machines cannot disambiguate meaning according to the context. Therefore, in current symbolic AI, we cannot rely on natural language to organically generate semantic relations like it happens in our mind. So how do we build a symbolic model today? In order to define concepts, we have to link them to URIs, Uniform Resource Identifier, or to web pages, like in referential semantics. But because referential semantics are inadequate to describe a network of relations, instead of relying on linguistic semantics, we have to impose semantic relations on concepts one by one. And this is why the design of knowledge graphs is so time-consuming, and why there is no general semantic interoperability of knowledge graphs across ontologies or domains, even if we use the same natural language, English, for example. Of course, I'm speaking here of interoperability at the conceptual level, not at the format level. In order to alleviate the shortcomings of current symbolic models, I have constructed a meta-language that has the same advantages as natural languages, namely an inherent mechanism for building semantic networks. But this meta-language does not have the disadvantages of the natural language, since IEML is unambiguous and calculable. So this meta-language is a non-ambiguous and computable semantic meta-language that includes a system of interdefinition, composition, and substitution of concepts. IEML has the expressive power of a natural language. You can say everything you want with it, but it has an algebraic structure. And of course, no natural language has an algebraic structure. Even if the grammar can be sometimes reduced to an algebraic structure, as Chomsky has shown. So basically, IEML is computable in its syntactic dimension, but also in its linguistic semantic dimension. And the semantic relations, in particular, its composition and substitution relations, are computable functions of its syntactic relations. See what I mean? The semantics is a computable function of syntax, because of course, if we want it to be computable, it has to rely on syntax. And the difficulty of inventing this language has been to build the semantics on a syntactic foundation in a completely univocal way. So there is a regular grammar that is recursive, and there is a dictionary of 3,000 words, and with these words that has been very carefully chosen, you can build any concept you want. Okay, those are very basic concepts, the semantic building blocks from which you can build anything you want. And what is interesting is that IEML is its own meta language, because each concept is automatically determined by composition and substitution relation with other concepts, and by the dictionary, and every word of the dictionary is defined by other words. So it is closed, but of course it is also translated into English, and as you can imagine from my accent, in French. This invention should facilitate. It's an invention of a philosopher. In fact, it's exactly the idea that Leibniz had when he was speaking of the universal characteristics. Okay. So a language that could facilitate computation on concepts and not only on numbers. And of course, it should facilitate the design of knowledge graphs and ontologies by ensuring semantic interoperability and by fostering collaborative design. Indeed, IEML is based on a vision of digital-based collective intelligence. So you understand, it is not an ontology. It is not a super ontology. It is a language. And with a natural language, you can design any ontology you want. There is no limitation. Okay. So what kind, and now I'm coming to the combination of neural and symbolic models. Because IEML allows an innovative and integrated architecture, overcoming the limitations and current divide of symbolic and neural models. So this, okay, no, I have, sorry. I have spoken without thinking about the the slide. I'm really sorry. Okay, that's it. That's it. So these slides introduce the new semantic architecture for knowledge management made possible by IEML, an architecture that brings together neural and symbolic domain and symbolic models. Now I'm going to comment on the red-orange central layer. You understand that the only thing that can generate all the concepts we need to express the complexity of knowledge domains while maintaining mutual understanding is a language, like a natural language, okay? But as we know, natural languages are irregular and ambiguous, and their semantics cannot be computed. Again, let me repeat, IEML is a univocal and formal algebraic language, unlike natural language, that can express any possible concept like in natural language. With its semantic relations densely woven in a built-in mechanism. So we can use IEML as a semantic metadata language to express any symbolic model, and we can do it in an interoperable way. Again, I mean conceptually interoperable. With IEML, all symbolic models can exchange knowledge modules, and reasoning across ontologies becomes the norm. This is an utopia, of course, but it's technically possible. Now I am speaking about the blue layers under and above the the central symbolic layer. How can neural models be used in this new architecture? They could automatically translate natural language models. No, they could automatically translate natural language into IEML with no extra work or learning for the layman. Neural models could even translate informal descriptions in natural language into formal models expressed in IEML. We will need a little bit of training to do this, of course. It's not immediate. Also, prompts expressed in IEML behind the scene would make data generation more controllable. And we could also use neural models to classify or label data automatically in IEML. Labels or tags expressed in IEML would support more efficient machine learning because the units or tokens taken into account would no longer be sound units like characters, syllables, and so on, sound units in natural language, but concepts generated by a semantic algebra. And I am coming to the end of this talk. So what are the main advantages of the integrated knowledge management architecture that I am describing? Symbolic and neural models would work together for the benefit of knowledge management. A common semantic coordinate system would help the pooling of models and data. Symbolic models would be interoperable and easier to design and formalize, and their design would be collaborative across domains. It would also improve intellectual productivity by allowing a partial automation of conceptualization. Can you imagine? Automation of conceptualization. And neural models would be based on data labeled in IEML and therefore be more transparent, explainable, and reliable. And this is important not only from a technical point of view, but also from an ethical point of view. Finally, this architecture would foster diversity and creative freedom, since the network of concepts of knowledge graph formulated in IEML can be differentiated and complexified at will. So some references for those who are interested. The scientific paper, I forgot to write the title of the scientific paper. The title is Semantic Computing with IEML. There is a book, there is a website, and for those who read French, it's the same article, but with different reviewers. So it's very interesting because the advices of the reviewers in French and English were very different. So it was two different papers. So thank you very much.
Thank you, Pierre. Thank you very